In Lecture 6.1, we learned how to compute work done by a constant force. For example, as illustrated in the earlier video, the work done by a man pushing a box at constant force F over the distance delta d is given by F times delta d. But not all applied force is going to be constant. In fact, realistically speaking, forces in everyday life are not constant. For example, let's recall the elastic spring force we learned in Chapter 5. The strength of such force depends on how much it is already stressed to begin with. Hence, applying a force to stress or compress a spring is never going to be constant. How are we going to compute the work done to stress or compress a spring then? If we plot the force versus amount of displacement from equilibrium, that is F versus x for spring force, it will look something like this. The slope of the plot is the spring constant, which indicates the stiffness of the spring. We discussed this in Lecture 5 before. What we shall note further is that spring force is a linear function of x, meaning that the force increases at constant rate with respect to the displacement. If we are now asked to compute the work done by such force to stress a spring by d, now let's think about it for a moment. When the spring is unstretched initially, that is x is 0, the force is also 0. By the time it has been stretched by d, the force is k times d. In between, the force increases at constant rate. Hence, if we are to compute the work done on or by the spring using the formula we learned in the beginning of this chapter, we shall replace the constant force by the average force to stretch a spring. It is easy to deduce this average force, because if it is initially 0 and it is finally k times d, and it increases linearly, the average will be exactly in between the two extremes, half of k times d. Hence, the work done by spring force is given by half k d squared. In the same manner as we derive gravitational potential energy, this equation becomes the formula for spring or elastic potential energy. If you remember, I presented the argument here in the exact same manner as I did when deriving displacement in motion with constant acceleration in Lecture 4.3. This argument works once again because the force involved varies at constant rate, just like the velocity involved varies at constant rate in accelerated motion. But in most cases, this is not the case. Just imagine yourself pushing the box as illustrated earlier. Perhaps you can apply a constant force or constantly increasing force over a short distance. But over a long distance, you may need to slow down after you are running out of breath, stop pushing to rest, and apply short bursts of force again, and so on. The fact is, in a real-life scenario, forces are changing at different rates, just like cars are speeding and slowing at different rates along expressway. So how do we account for work by such forces? The answer lies in the calculus of integration. This will be left for discussion in our face-to-face tutorial session of this chapter.